In the last video we saw that we could use this limit definition of the derivative to find the derivative of a specific function at any point and then use that to find the slope of the curve at any point on that curve. However, if we had to always use the limit definition to find derivatives, then derivatives wouldn't be very useful because it would be too time consuming to find derivatives that way. So what we need to do is find some derivative formulas to make it easy to find derivatives. Well, in the last video we saw how to find the derivative of the function f of x equals x squared using the limit definition, and to do that we had to expand the expression x plus h squared, which gave us this expression. If we had to find the derivative of g of x equals x cubed, what we would have to do is expand the expression x plus h cubed, which would be this expression right here, but as you can see, if the power on x plus h gets bigger and bigger and bigger, that becomes more and more time consuming. So we want to find a general way to find the derivative of x to a power. So what we want to do is find a general formula for the derivative of f of x equals x to the n, and we're going to call that formula that we're going to find the power rule. So let's see how to come up with that rule. So we're going to use Pascal's triangle to help us out. Pascal's triangle is easily calculated. What we do is to find the number in the row below, we take the two numbers above that to the left and right and add them together. So you can see how we get the 2 here, the 3's here and here, the 4's here and here, and the 6 here. And you can also see that the next row should be what? 1, 5, 10, 10, 5, and 1. Now these numbers that we have here give us the coefficients of the expansion of the binomial x plus h to the n. So let's see what we mean by that. So what we've done here is we have expanded x plus h to the powers 0, 1, 2, 3, 4, and 5. And we want to show that it has the coefficients given by Pascal's triangle. So the first expression has coefficients of 1 and 1. The next expression has coefficients 1, 2, and 1. The next one, coefficients 1, 3, 3 and 1, 1, 4, 6, 4, 1. We also want to notice what happens to the powers of x when we expand the binomial and the powers of h. So let's take a look at x plus h cubed and note that the powers of x start at 3, go to 2, go to 1, and in this term the power of x is 0, whereas the powers of h increase. So in this term the power of h is 0, here the power of h is 1, here it's 2, and here the power of h is 3. So summarizing, so the powers of x descend from n to 0, and the powers of h ascend from 0 to n, and this is what we saw when we took a look at x cubed. We can see it also in x plus h to the fourth. Powers of x are 4, 3, 2, 1, 0, and the powers of h are 0, 1, 2, 3, and 4. So just one more example. If we wanted to expand x plus h to the 7th, let's put the x's and the h in first. The x's and the h's in first, so we have x to the 7th, x to the 6th, h, x to the 5th, h squared, x to the 4th, h cubed. Notice that the powers always sum up to 7, x to the 3rd, h to the 4th, x squared h to the fifth, x h to the sixth, and h to the seventh, and then we're going to put in the coefficients coming from this last row of Pascal's triangle, and so they are 1, 7, 21, 35, 35, 21, 7, and 1. So if we wanted to find the derivative of x to the seventh using the limit definition, we could do it using this binomial expansion of x plus h to the seventh, and you'll find that you will have a problem on your test like that. But our main objective here is to find a general formula. So let's take a look at, or let's see how we can generalize what we've just learned. So what we want to notice is that the coefficient of the first term in the expansion is always 1, and the coefficient of the second term in the expansion is always the power of n. And so when we expand x plus h to the n, here's what we get for the first two terms. So I've actually put the first three terms up here, but we really only need to pay attention to the first two terms, and we're going to use them in this formula we're going to develop. I put the third term in just to show that the same pattern is used in expanding x plus h to the n. Notice that x is dropping in power one more in this term, and the h is increasing one power. And we have this coefficient here, but we're not going to talk about how that's obtained. So let's try to use the limit definition of the derivative for x plus h to the n. Okay, so there's a lot written here. Let's see what's going on. So we've applied the limit definition of the derivative to the function x to the n. So we're expanding x plus h to the n minus x to the n, and then subtracting x to the n. So when we expand x plus h to the n, we only need to look at the first two terms, which we just identified on the previous slide, these two terms. And then all of the terms after that for the expansion, we're going to characterize them as just terms where the power of h is greater than or equal to 2. That's all we need to note about them. So let's make sure we understand why that is. In this term, the power of h is 0. In this term, the power of h is 1. And all the remaining terms will have higher powers of h, thus the greater than or equal to 2. So remember what our objective is in finding a limit when we have a 0 in the denominator. We're going to try and cancel that 0 in the denominator out by pairing it up with an h factor in the numerator. So first thing we notice is that the x to the n's in the numerator are going to cancel out. So let's see where we stand then. So all the terms in the numerator have an h in them, and we're going to factor an h out of them. So once we do that, we can pair up this h factor in the denominator with this h in the numerator, cancel the h out. We're canceling the 0 over 0 part of the limit out, and we then have a plug it in case 1 type of limit. So after we cancel the h out, we notice that what remains here are terms, all of which have an h in them, and since h is going to 0, all of these terms are going to go to 0, and we have our result, nx to the n minus 1. So the derivative of x to the n is nx to the n minus 1. We usually say that in words to get make sure we have that clear. What we're doing here is we take the power on x, bring it down in front, and then reduce this power by 1. So in words, bring the power down to the front as a coefficient and reduce the power by 1. So let's practice using this a couple of times. So if f of x is x to the 7th, f prime of x is 7x to the 6th. If g of x is x to the 9th, g prime is 9x to the 8th. If h of x is x to the pi, h prime of x is pi x to the pi minus 1. And let's expand the rule just a little bit. So our j of x has coefficients already, and in this case when we bring the 5 power down we must multiply that by the 2 to give us 10x to the 4th. We preserve the minus sign between the terms, multiply the power 2 on the x in the second term by the 3 to get 6, and reduce its power by 1 to get 1. And one final one, our k prime of x is going to be 4x cubed minus 18x squared. When we take the derivative of the 18, so when we take the derivative of this last term, denoting the power on the x as 0, we bring the 0 down, multiplying it by the 18, and so we get, as our last term, a 0. And that's because the coefficient is 0. We don't really need to note what the power of x is. It's actually x to the minus 1, but what we should note is that that term is really just a 0 term, so we can remove this x to the minus 1 part of it. So one final summation, that the power rule for f of x equals x to the n, f prime is n, x to the n minus 1, as we saw in the examples on the previous slide. It allows us to take the derivative of any polynomial function as long as we apply it repeatedly to the terms involved. Our next video is going to be on the product rule. It turns out that when we have functions multiplied together, even though we can multiply them out, that turns out to be too time-consuming in most cases, and so we want a rule for taking the derivative without having to multiply the functions out.